This section is saying, well, what if you know the probability of success? Just in general, you know that there's a 50% chance of succeeding, such as flipping a coin. What's the probability of succeeding twice? What's the probability of succeeding 7 times? What's the probability of succeeding 2 to 5 times, given that you tried it 10 times? Those are the types of questions that we're going to be answering through the binomial distribution. Now, binomial, if we break down the words, bi, the prefix means 2. So there's always going to be 2 options. You're either going to succeed or you're going to fail. Now, when I hear those 2 words, I think of success as a positive thing and failure as a negative thing. Statistics doesn't see it that way. If I'm talking about the number of fatalities in Florida, a success would be someone dying. That's not a nice thing, but that's what we're testing. So a success is not what is the better thing, it's just what we're looking at. If we're looking at the number of people that have been laid off during the pandemic, a success is that you lost your job. If we're talking about the number of people that got their jobs back, a success is now getting your job back. So it doesn't really matter if it's good or not. It's just what we're testing is a success. The trials are the number of people that we're talking to. So with the binomial, we're always going to have a success. We're always going to have a failure. Combined, those 2 successes will always be 100% because you're either going to succeed or you fail. There's no other option in there. Another example of what would be a binomial distribution is that if we had this made up TV show and they're trying to spin the wheel of good fortune, there's a roulette wheel with 36 slots. One has a wedge of gold. And if you land on that gold, then you win $50,000. Now, as a producer, you would not want to just create a show and then see how it goes. You want to know, well, what's the probability of us losing how much money? What's the chances that we have this many winners? Because if all of a sudden you just create a game and then people are winning all the time, you're going to go bankrupt. They actually have done studies with casinos, and some of them are somewhat rigged. And what they do is that they change it so that there's a greater chance of people winning on opening nights. So people get these big winners, and then people are more apt to like, oh, I can win too. And then things start to decline. Keene has a new casino that just came in with real gambling, all that stuff. And every week they say on how much money they gave out. Like last week, they gave $400,000 to the people that gambled there. The week before that, it was $250,000. If you go this Monday, you get a 7-quart crock pot without gambling. I'm like, wait, what? So they're saying that they're giving out all this money, but they're trying to give away free stuff to get in there because they are trying to convince people to gamble there. But they know what they're doing. They know how much money they're losing. They know what they're willing to do because they figured it all out. That's kind of the same thing here, is that you want to make sure that it's enticing enough to do it, but the odds are still in your favor. They may have given out $400,000, but how much money did they make? So we're going to use the binomial distribution to figure out that if we know the probability of success, what are the chances that we are going to have to pay 3 of 100 people? So if they have to pay money to go to this game show, does 97 people failing pay more for us than 3 people succeeding? And then what's the probability of that happening? And are we willing to risk that sort of probability? So that's kind of the types of questions that we're going to be trying to answer through the binomial distribution. Now, where this chapter is going to get confusing is that we are going to be having 4 different probability distributions. This is the second of the 4. So when you read a problem, you have to be able to differentiate, is this binomial? Is it just a probability distribution? Is it geometric? Or is it our Poisson distribution? And there's going to be certain attributes that we're going to need to look at. These 5 here are the 5 attributes to a binomial experiment, where we have to use the binomial distribution. So the first attribute of a binomial experiment is that we have a fixed number of trials. So we know that we are trying a certain number of times. In the previous example with the Wheel of Good Fortune, we're trying 100 times because there are 100 contestants. If I was flipping a coin 10 times, I know I'm stopping after the 10th flip. We always try to denote the number of trials as n. So the total number of trials is n. The n trials are always going to be independent, meaning if you succeed the first time, it does not affect your chances of doing it again. So this wheel of good fortune example, if we were to take out a wedge every time someone landed on a black, we'll say, that's no longer independent because the second person to spin it has a greater chance of winning than the first person did. And then if two people failed, then the third person has a greater chance, things like that. So it has to be independent, meaning it can be repeated under identical conditions. Every trial only has two outcomes. Either you succeed or you fail. Again, that's kind of arbitrary. It's what we're focusing on. For each individual trial, the probability of success is the same. That's the concept of it being independent. If you know the probability of success, then it's going to be the same every single time. In the Wheel of Good Fortune, there are 36 wedges that exist. One pays out, so there's a 1 in 36 chance of succeeding. So that would be our probability of success. The letter P is usually the symbol for the probability of success. So in this book, they use P's and Q's, where P is the probability of success and Q is the probability of failure. Now, since these are the only two options, the probability of succeeding and failing is the same. So they add up to 100% of the outcomes. So if you know the probability of success by subtracting from 100%, you get the probability of failure. And then the last thing is knowing what you're trying to look for. And the central problem of a binomial experiment is always to find out the probability of success out of n trials. So we're always going to deal with probabilities. And we want to know what's the probability of succeeding this many times out of this many trials. All right. And if I'm ever going too fast, just please make sure to let me know. Going to kind of bypass this slide. It's just referring to, does replacement always mean dependent? It is possible that common sense tells us that things aren't independent. Like this example here is that there are 10,000 bills of a huge, I'm sorry, of a large university. So if they select 20 tuition bills at random out of the 10,000, they want to know what's the probability of there being an error in the tuition bill. So even though you're using 20 and once you use that tuition bill, you discard it, technically you'd be down to 9,999, but that is so small that it would still be independent. So it is still possible that if common sense tells you, well, it is changing a little bit, it might not be statistically relevant. But we don't really come into that problem. It's just more of a general thing. I'm going to show you how we would want to do this by hand for those that want to do that, but I'm then going to show you actually how to do it on Google Sheets. So if you see it by hand, you're like, I like that, I want to do that, then this is what you're going to want to do. If you look at it and say that's way too much work, I don't want to do that. One, I think you're right, and two, I would definitely go with Google Sheets over this. So the example that we're going to focus on is you have 3 multiple choice questions left to do. So you're a junior, you're taking the SATs, a little timer comes up, you have 5 minutes left, and that's ticking down, and now you only have 2 seconds left, and you have 3 multiple choice questions left to do. Each question has 4 suggested answers, and only one of the answers is correct. You have 5 seconds to do these 3 questions, so you mark your answers without even reading the questions. Assuming your answers are randomly selected, what is the probability that you get 0, 1, 2, or all 3 questions correct? We're going to use the binomial distribution to figure this out because you have 2 options, either you're right or you're wrong. Your probability of success is 1 in 4 because only 1 out of the 4 questions is the correct answer. And we're going to do this 1, 2, 3, 4 times, because we want to know the probability of 0, probability of 1, probability of 2, and then probability of all 3. So if you wanted to do this by hand, this is the probability of getting one of the answers correct out of the 3 questions. The only way to get one right is you would either succeed on the first one and fail on the other 2. You could fail on the first one, succeed on the second, fail on the third, or you could fail and then succeed. So those are the 3 different permutations you could have for getting 1 out of the 3 correct. And so you'd have to figure out, well, what's the probability of success? What's the probability of failure? Again, 1 out of 4 and 3 out of 4. That's where this 25% and 75% come from. And you would see that succeeding and failing twice would be P times Q, because you succeed and you fail, or P times Q squared. There are 3 ways that could happen. So you multiply P times Q squared by 3, and that there is a 42.2% chance that you would get exactly 1 out of 3 right, given that there was 4 choices and there was a 25% chance of getting this all correct. And then if you had to do it for 0, 2, and 3, you're doing all this again. Gets to be a pain in the butt. If you were more of a formula person, right here is the formula. You would take the number of combinations. So you'd have to do the whole NCR thing, times the probability of success, times the probability of failure, and then you would have your exponents associated with those. Once again, this is a pain in the butt. You are not responsible for using this formula. But if you wish to do this by hand, this is what you want to use. So we've already gone over how to do combinations. So you do the combin, parentheses, n comma r, and then it would be the probability of success to the number of times that you want to succeed, and then the probability of failure of the difference of the number of times you tried and succeeded. So the number of times you failed, really. So in the example above, there's 3 different ways, 3 different combinations, and then the probability of success, you'd only succeed once and you're failing twice. So that's the formula up above. To do it on Google Sheets. So let's just go ahead and delete these. This is a different example that I was going to use, but let's use the one that's applicable. So the command that we're going to use is binom dist. Now, as with some of the other things, I don't know why, but Google Sheets has multiple commands for the same thing. So when I type in equals binom dist, that's not populating it. It's not giving me the other options. The other one that it has is binom period dist. So it does the same thing. I'm not sure why it's not giving me the options as it normally does. There's also an inverse binomial, and there's a few others that we're not going to use. But the 2 that you can use are going to be the binom dist and the binom period dist. But the first option is going to be the binom dist as up here. So I'll do the 1 success first so that we can see that it matches up to what I had on the slideshow. So I'm going to do equals binomial distribution, open my parenthesis, and I'm going to click on this question mark just so you can see what it's asking for. So it's going to break down, hey, we need these 4 things. The first one is the number of successes. Now we want specifically 1 success. So I'm going to type in 1, comma. Now it wants the number of trials. So we have 3 questions that we're answering. So I'm going to type in 3 and then comma. Then it wants to know what is the probability of success. So there is a 1 in 4 chance. So you could write 1 divided by 4, or since we know the decimal equivalent, I'm going to write 0.25. And then this last part is going to be the most confusing from what I found from people. And that will be whether it is cumulative or not. Now, what cumulative means is that, and this is the same thing with the tables that we would use, the calculator we would use, and most other things that calculate a distribution, it always counts down. I'm not quite sure why it only does it this way, but if I said true, that means that it is going to add the probability of succeeding once with the probability of succeeding 0 times. If I put a 4 for the number of successes, I'm sorry, a 3 for the number of successes, it is going to be 100% because it is going to add the probability of succeeding 3, 2, 1, and 0 times. So where it says cumulative, if you want it to count down, we're going to write true. If you want it exactly at that success, we're going to write false. In this case, I want one success and one success only, so I'm going to type in the word false. And it gives me the 0.42, and then this is a little more exact than the calculation I had on my slide because I had rounded up to the nearest thousandths place, but that is the probability of succeeding once. Now, some of these problems may ask you to find multiple probabilities, kind of like the one in the slideshow. What's nice is that we can just take this, copy it, and then we can paste it in the next cell. And up in our function bar, we can change the 1 to a 0. Now it's the same probability, but I can see that I now have 0 successes out of 3 tries, 25% chance, and false. Do it again, but now for 2, and then do it again, and now for 3. Now these are all the possible options for succeeding. So in theory, if I added them all together, it should equal 100%, which it does. So I know that this is working because it is 100% of all the possibilities. So how I would read this is that to succeed 0 times, there's a 42% chance of that happening. To succeed once, there's a 42% chance of it happening. To succeed twice, so that's getting 2 out of 3 completely right, there's a 14% chance of that happening. And then to succeed all 3 times, there is a 1.5 or about a 2% chance of that happening. So using the binomial distribution, I know the probability of succeeding 0 times, 1 time, 2 times, or 3 times. Now, what if I wanted to succeed? I don't know, I'm fine with, I don't want to get all 3 right because then for whatever reason, but maybe I want to get 0, 1, and 2 questions right. So I'm okay with getting them all wrong, or I want 1 right or 2 right. For some reason, I don't want all 3 right. So I could, now that I have these, add them all up. That would probably be the easiest point at this point. But what if the only question was, what's the probability of getting 0 or 1 or 2 right? I wouldn't want to generate all these probabilities just to add them. So since we're counting down, I'm going to calculate using the binomial distribution 0 to 2 successes. And to do that, I'm going to do the binomial distribution. And I'm going to use the largest number of successes. So 2 successes out of 3, there's a 25% chance of doing it. And now I'm going to use the true command. So now what I'm telling Google Sheets is I want you to start at 2 successes and add 2, 1, and 0 together. And it is getting 98.4%, which is the same thing as adding these 3 probabilities together. But again, if you were only asked 0, 1, or 2, it would make more sense to do this 1 command than doing these 3 commands and then adding them all together. What if I wanted to get something a little more practical? I wanted to have 2 or 3 successes. So that means I'm fine with 2 or 3. Now I'm asking Google Sheets now to count up 2 successes to 3 successes. And Google Sheets is going to say, no, I don't want to do that because it only counts down. So this is going to be a situation. Instead, I'm going to calculate what I don't want, and I'm going to subtract it from 100%. So my calculation is going to be 100% minus 0 to 1 successes. So again, I don't want 0 or 1, so I'm going to let Google Sheets calculate that because that can count down. And then by subtracting from 100%, I can find everything that I do want. So I'm going to do equals 1 minus the binomial distribution of 1, 3, 0.25, true. So what I have before I finish off the word true is that starting at 1, it's going to count down to 0. And then whatever that probability is, I'm going to subtract it from 100%, and that should give me the 2 to 3, which would be 15.65, which again, if I had done them all out, I can just add them together. Now, if you were thinking to yourself, well, I'll just do them out every time because it's easy to add them together, you are right. That is a possibility. But if the sample size was maybe 100, you probably wouldn't want to do 100 different probabilities to add 55 to 60 successes. You'd rather just do one command with the binomial distribution. So we're going to practice more of this tomorrow, of just working with word problems, reading them, and understanding how we're going to plug into the binomial distribution and all that stuff. And usually once you get the flow of how it works, it makes sense. And what's kind of nice is that the logic of the number of successes is the same for the binomial, the geometric, the Poisson, and the normal distribution. So all the distributions we're going to be using is using this sort of content. So it's worth it to put in the effort now to kind of understand it, because for the next 2 chapters, we're going to be using this skill. So it won't go away anytime soon.